Okay, well, happy Monday. So today I'd like to finish the unit on centrifugal settlers, and we'll look at electrostatic precipitators. So let's start by addressing the question. Suppose we want to remove even smaller particles. And let's just use the equation I gave the other day for the cut diameter. So this equation for the cut diameter, if we wish to remove smaller particles, so we want a smaller cut diameter, what can we do? We want to improve efficiency. We want to, for those smaller particles, what can we do to accomplish that? W sub I, the inlet width. How can we change the inlet width in a way that will decrease the cut diameter? Make it smaller, exactly. So we can decrease the width. How about the number of turns? How can we change the number of turns? So the number of turns was equal to 1 over H LB plus LC over 2. H is the inlet height, L sub B is the body length, and L sub C is the cone length. So, okay, we increase the number of turns. In order to do that, then we would need to decrease the height and increase the body length and the cone length. And we can also increase the velocity. Problem with all of these is changing one impacts another. So we change the width, we decrease that, that's going to increase the inlet velocity. That will increase the efficiency, but it will also increase the pressure drop, and the pressure drop is proportional to the square of the velocity. So small changes in velocity will have a significant increase in the pressure drop, which means that this will increase the cost. So the problem we have is we can accomplish these, but if we do that, big is that is going to decrease flow. So if it decreases the flow rate, we can't treat as much gas. The way that that is dealt with is with what is referred to as a multi-cyclone, and that's what you see in the picture here. What is created is a unit with many smaller cyclones running in parallel so that they can treat a larger flow. So you have basically what you see here, this large metal box. Inside that is not one cyclone, but many cyclones. And the flow is divided into those multiple cyclones. So there's a manifold to distribute the flow across the numerous cyclones. The pressure drop, as I mentioned, is a function of the square of the inlet velocity. This term here is typically referred to as the velocity head, and H sub V is the pressure drop expressed in the number of velocity heads. The K is a function of the cyclone separator. H and W are the height and width that we used W sub I, so just add the I. So it's the height times the width, and D sub E is the exit diameter. So that pressure drop is just the product of HV times the velocity head. And typically, this K value ranges between about 12 to 18. Now, the fluid power requirement is equal to your flow rate, so it's your gas flow rate, times this differential pressure. Now, we need a fan or a blower to overcome the pressure drop, unless the system's under pressure, which typically is not the case. And we have two choices. We can put a blower before the cyclone separator, or we can put it after. We put it before. We have any problems? What would be a problem of putting the blower before the cyclone separator? Okay, so we've got a cyclone separator. We can put the blower before, or we can put it after. What's an issue with putting it before? Gas is dirty, so if we put it before, then it's likely that that particulate matter in the gas can get into the bearings, can collect on the blades. That's going to throw the blower out of balance. You're going to have excessive vibration. That's going to be detrimental to the bearings. So you can have mechanical problems for that reason. You can put the blower after the cyclone. Now it's cleaner gas that passes across the blower. You have fewer maintenance problems, but then the cyclone is operating under weak vacuum. And if there are leaks in the seals, then you're likely to entrain some of that particulate that you've removed back into the gas stream. So you get poor removal. So there's advantages and disadvantages of both. In both cases, the system really does need to be maintained in order for the cyclone to work properly. So let's look at the previous example. So in this case, what we'll do is we'll calculate the pressure drop and the power. So you're given a K value by the manufacturer. The parameters that we have are identical to before. What we will use are the dimensions from the FE handbook that I provided you with last week. And we're using a body diameter of 1 meter. So if you recall, the information in that table really are ratios. So since I've used a body diameter of 1 meter, we can use the dimensions that are provided. So let's look at this problem here. We have the equation HV is equal to K H times WI over D sub E squared. And we said H is equal to 0.5 meters. W sub I is equal to 0.25 meters. And D sub E is equal to 0.5 meters. So that information was given in the previous problem. So H sub V, or the pressure drop expressed in the number of inlet velocity heads, is equal to 15. So the K was given, times 0.5 meters, times 0.25 meters, divided by 0.5 meters squared. And that is equal to 7.5. The inlet velocity was given as 1,200 meters per minute. We need this in seconds, and that is 20 meters per second, which is actually identical to what we should be what we calculated previously. The pressure drop is equal to 1/2 times the density of the gas times V sub I squared times HV. And that is equal to 1/2. The density of the gas from the previous problem is 1.18 kilograms per cubic meter. The velocity is 20 meters per second squared. Multiply that by 7.5, and I'm going to multiply by a conversion. There is 1 kilogram per meter second squared per Newton. And if I multiply this, I have 1,515 newtons per meter squared. And that is equal to 1.515 kilopascals. Pascals is a Newton meter. I just converted this to kilopascals. So that is delta P. That's the pressure drop. The fluid power requirement is equal to Q times delta P. Q was given as 150 meters cubed per minute. We'll convert that, apologize for the extra lines, seconds per minute, multiplied by 1.51. So we're going to multiply by, and Newton meter squared. And this is equal to 3,788 Newton meter second, which is a joule per second, which is 3.8 kilowatts. So that's the power requirement. In order to determine the power for the fan and motor, the fan and motor won't be 100% efficient. Let's use a 70% efficiency, which is reasonable. So if we have 3.8 kilowatts divided by 0.7, that is equal to 5.4 kilowatts, or about 7.3 horsepower. Let's give it in US units. Okay, so we need about 5.5 kilowatts. But what we were able to calculate here was the pressure drop. We're able to calculate the fluid power requirement, and then we're able to calculate the power requirement that we need to supply to the fan and motor to operate this system. And just to give you a sense of the size, these range from typical industrial units to looking at 6 to 8, 9, 10 inches inlet velocity, somewhere between 50 to 60 feet per second. And you can kind of see the size of one of these units on the back of a flatbed. Any questions about cyclone separators?